Just like water, alcohols are acidic compounds. The acidity comes from the polarized OH bond, which can react with the base, and owing to the high electronegativity of oxygen, it can relatively comfortably leave oxygen negatively charged and abstract the proton. In order to determine the value of this acidity, we use the acidity constant, which gives us R minus and H2O plus here, and then we quantify this relationship by having the constant for this equilibrium over ROH. But most commonly these are expressed in terms of pK, which is the negative log of Ka, and because it's a negative log, the lower the pK value, the stronger the acid. If we look at the acidities of alcohol, you see that methanol has a pKa 15.5, ethanol is pretty much the same, 50.9. If we have trichloroethanol, this is 14.3, T-butanol, about 18, and then compounds like water, about 15.7, acetic acid is about 4.8, HCl is minus 2.2, and so on. So put in context, alcohols are relatively close in acidity to water, and they're much weaker acids than HCl or acetic. But within themselves, the alcohols vary quite a bit. And these effects are caused by Cl in trichloroethanol, which is electron withdrawing substituent, which means it pulls electrons from OH bond and makes hydrogen even more positive, so it makes it easier for it to leave in acidic reaction. On the other hand, T-butanol has metal groups which are electron donating. As we've seen, the metal groups have a lot of extra electrons they can donate to the center, so they strengthen the CO bond, the OH bond, and thus make hydrogen departure harder. Okay? And so therefore these effects are considered. Now, the alcohols, owing to their acidity, they can react with sodium and other alkaline metals to give directly alkoxide with the evolution of hydrogen. Well, this reaction looks like an acid-base reaction. It's basically a redox reaction because sodium goes from sodium 0 here to sodium plus, while hydrogen goes from H plus to 1/2 of H2, which is 0. So this is a redox reaction. But despite that, it's a reaction that's very commonly used to produce alkoxides, which are strong bases. If you ever wondered how did we get that potassium T-butoxide that we use in all these elimination reactions, well, we simply just dunk some potassium into T-butanol. Because T-butanol is relatively bulky, it reacts with potassium very slowly. If you throw potassium into water, it was very likely it will catch fire, that the hydrogen released will catch fire. If you do that in methanol, methanol it will still be pretty vigorous. In T-butanol, the reaction is already much subsided and it can be perfectly controlled. And this is how we get potassium T-butoxide, which then remains dissolved in T-butanol, and this is how we use that mixture that is often seen in E2 reactions. Phenols are more acidic than alcohol. If you look at the phenol itself, the pKa here is several orders of magnitude lower. The pKa is several orders of magnitude higher, which means the pKa is several units lower, it's just about 10. And the reason for that comes from the stability of the phenoxide anion. Phenoxide anion is this species, and it is resonance stabilized. It has several resonance structures where we can push this charge all around the ring. And once again, and since this anion is so resonance stabilized, it means that its production is favorable compared to alkoxides, and therefore phenol itself is a stronger acid. To sum this up, alcohols are acidic. Their acidity depends on a number of factors, on presence of electron donating and electron withdrawing groups, as well as on resonance stabilization of phenols. The unresonance stabilized alcohols are comparable in their acidity to water, which is about 15, and this reaction is used a lot to produce alkoxides. Well, typically the production of alkoxides themselves is not an acid-base reaction, instead a redox reaction with an alkaline metal and an alcohol.